Okay, class, welcome to another lecture. Today we're talking about proof by cases. And it's not some grand new idea. It's going to make some pretty good sense in a second. So the idea, first I got to use a pen. Okay, so the idea is that when we have something like this, so it's sort of easiest to see through an example. So when we have something like, think of a statement like this. If n is an integer, then n squared plus n is even. So when we have something like this, the idea is that we can prove it by breaking the hypothesis up into cases. That's where the name comes from. And what this means is that the hypothesis has to be able to be broken into cases, which is true here, and I'll show you how in a second. Okay. So you look at the hypothesis and you say, can I think about that in a different way? Can I like break it up into smaller pieces, sort of? So the way to think about it is n can be an integer. Is there another way I can say that in pieces? Yes, there is. I can break up the integers in lots of ways, but one way is that I could say it's either even or n could be odd. And breaking it up in this way is the same as saying any integer, right? Because if it's even, that's half of them. If it's odd, that's the other half. That's all of them. So I'm not missing any integers. So this needs to include all cases. Otherwise, you're not proving it, because you're not proving for every integer that this happens. You're proving for some. So when you break it up into cases, the cases have to actually cover the entire hypothesis. So then what we can do is you can just prove it in each case. You can prove by proving that the conclusion holds in each case separately. I never know how to spell separately, but that looks fine. So what I'm saying is you turn this statement into really two statements. If n is even, then n squared plus n is even. And if n is odd, it still happens. So all we've done is split the hypothesis up into two pieces here that cover the entire hypothesis of n being any integer. And then proving both of these automatically proves the statement for you. Okay. Where did my next notes go? Oops, here it is. Okay. So if you really want to think about why this is allowed, I hope that's already convincing, but if you really want to like get into it, this is allowed because of something we proved. I forget if it was in a lecture or in the lecture problems, but it's really just this little thing. It's that if I do P or Q, if that, then R, that's logically equivalent to saying that P implies R and Q implies R separately. Oops, that's not the implies symbol. If Q, then R. So this is exactly what's going on. This is saying that if my hypothesis can be broken into OR pieces, sometimes it doesn't, it's not told to you that it can be broken into pieces or pieces, like n being an integer is the same as n being even or n being odd. But if you can do that, if you can break it up into ORs, then you can prove it in this other way. And that's really what proof by cases is. It's breaking up the hypothesis into OR pieces. And you can extend this to more OR pieces. So this also works for more ORs. So if you say, like, I'm gonna run out of letters, but P or Q or R, what's the next letter? S, then that's gonna be the same as doing each one. P implies S, and Q implies S, and R implies S. But it's really just the same idea of the hypothesis is being broken into all possible cases. Okay, so shall we do an example? Yeah, let's do the example I have up there. So the one I said earlier, if n is an integer, then n squared plus n is even. Okay, so I'll rewrite it here. We'll prove if n is an integer, then n squared plus n is even by cases. Now, first of all, why would you want to do cases? Well, what cases do is they give you more information to work with. So if I didn't try to do cases and I just said, okay, I have an integer, now I'll square it and add it to itself. Why is that even? There's nothing I can do because I don't have a nice little, oh, n equals blank. So I'll plug that in and see what happens. If n is just any integer, then I don't get that luxury. But by breaking it into cases, I get little formulas to pop out. And that's the idea. Okay, so what we do in a proof by cases is we just say that we're doing that, and then some people like to number it. So they say like case one, something like that. Case one is that if n is even, then we're going to prove n squared plus n is even. Whoops, not n squared plus n squared. Okay, so now it's like a mini proof instead of a proof. So now we're just focusing on this. So how do I prove a statement like this? Well, I know n is even. That means I just say exactly what that means. This means that n equals 2 times a number for some integer x. Okay, so now this is the whole point. Because I know something more specific about n, not just that it's any integer, but that it's even, now I can actually look at n squared plus n and do something. I can do this. And I can see why this is even. And it's because now I can factor out a 2. So this is an even number because it's 2 times an integer. And we've done that kind of proof enough to just stop there. Okay, but now the case 2, so now I just prove, well, okay, that covers all the situations in which n is an even integer, but now what if n is odd? That's the other case. If n is odd, then still the conclusion is not changing. So I'm still trying to show that n squared plus n is even. That's case 2. So now again, it's like a little mini proof of just this little statement. Okay, so since n is even, or sorry, now it's odd, what do I know about that? I know that that means n equals some 2x plus a number, sorry, 2 times a number plus 1 for some integer x. And once again, now I have information about n, so I can actually say a lot more about n squared plus n. And I do this, and now it's going to just turn out to just be some nice algebra to make this be an even number. Let's see, 4x squared plus 4x plus 1 plus 2x plus 1. Yep, that's 2 factors out of everything, as long as you are careful. Then it'll work out, which is even. And then if you want a nice concluding sentence, you can write something like this. So since n squared plus n is even, when either n is even or odd, this means n squared plus n. So now I'm just summarizing the cases, is even no matter what integer I started with. Okay, and that's the end of the proof. All right, so hopefully not too bad. I don't know how many of these I want to try because there's other stuff to do, but we can do one more. All right. So for any integer n, how about this? N squared plus, or nope, minus 5n plus 7 is odd. Okay, so now we know, because this is in the proof by cases section, it's definitely going to be a proof by cases. So we're just going to jump right into it this time. So case 1, if n is even, I'm not going to write the whole case down, I'm just going to get going on the proof. So if n is even, then n equals 2x plus, 2x4 some integer x. Then what happens? Then n squared minus 5n plus 7 is going to look hopefully like an even number. Sorry, an odd number this time. 2x squared minus 5 times 2x plus 7. And I believe it does because a 2 will factor out of the first two terms. So that will make this be odd automatically. But if you really want to be extra fancy, you actually have to do a small little trick to make it look just like the definition. So I have to think about 6 as being, 7 as 6 plus 1. That way I can do 2 times something plus 1, which is odd. And that satisfies the definition of being odd. Okay, so case 2, if n is odd to start with, then what happens? N equals 2x plus 1 instead, some integer x. So now I just do the same thing. N squared minus 5n plus 7 is going to just look a little bit different. 2x plus 1 squared minus 5 times 2x plus 1. Now you just use some magic algebra. 4x squared plus 4x plus 1 minus 10x plus minus 5 plus 7. Hopefully this is odd. It should be. I should be able to take a 2 out of everything. That's going to be negative 6x. So I'll take out the 2 and get negative 3x. 8 minus 5 is 3, which I can write as 2 plus 1. So I'm skipping a lot of steps there, so verify that. Okay, and then so this is 2 times a number plus 1, so it's odd, or that the number is an integer that you're multiplying by 2. Okay, so again, this ends the proof. So this shows n squared minus 5n plus 7 is odd for any integer n. Again, the reason it's working is because I've covered all possible cases. I've covered all the evens and all the odds. That's all the integers together. Now, if this said n squared minus 5n plus 7 was odd for any real number n, this wouldn't make sense because this doesn't cover all the real numbers. It just covers all the integers, which can be broken up into even and odds. So we're not going to do much of this, but you'll see this in another class, probably if you take like something called number theory. So you can break integers up into many different ways. So here's the first way we just have seen how to break up integers. So you could think of them as even and odd. But what you should really think about is divisible by 2 and not divisible by 2, because then you can extend this. Numbers can be divisible by 3, or they can be divisible by 3 but have a remainder of 1, or have a remainder of 2. So if you're dividing by 2, there's even and odd. But if you're dividing by 3, there's not just divisible by 3 versus not divisible by 3. There is remainder 1, remainder 2, or no remainder, which is divisible by 3. And then this pattern continues. So we're not going to do any examples, I don't think. Maybe on the lecture problems there'll be some. But this is basically saying like, okay, maybe breaking up into even and odd doesn't work. So maybe you break it up into 3 pieces. So this breaks up the integers in a different way, into thirds. I guess thirds isn't really the good word for that, but basically you get 3 cases to prove and 4 cases and so on. So if you make a claim about all integers, one technique is to try to break it up in different ways. And okay, even and odd doesn't work, try something else. Okay, but we are gonna look at something else. I might put something like that on the lecture problems instead. Okay, so what we're gonna look at is a new definition to play around with. It's always fun. It's a definition that is very, very important if you ever take the class real analysis. It's gonna come up a lot. So, and if you're watching this, you're probably gonna have to take real analysis. Okay, so for a real number, x, we're gonna define this new yet very old concept that you've seen before, but never thought of in this way probably. We define this guy, x with bars around it, called absolute value of x. Now, if you're like me, when you grew up and learned about this the first time, your teacher probably just said, turns everything positive. That's what the absolute value of x is. Everything becomes positive. But that's like child's play. That's not really the definition. It's really a piecewise function, which means you write it as this very fancy curly bracket that you have to have a PhD to draw correctly. So you do that, and the pieces of the piecewise function go on the left here, and then when you use each piece goes over here. So this is the actual definition of absolute value, and it does give you the same thing if you just think about it. It's like it makes everything positive, but this is better because it breaks up into cases. So what this is saying is, if the number you plug in is already positive, if this happens, if the number you plug in is already positive or just 0, then the answer you get is just that number. So that's why absolute value of 5 is 5, because 5 is already bigger than or equal to 0, so you don't need to do anything to it. But if, oops, I didn't put if down here. It should be there, if there also. But if you plug in a negative number, how do you make something be positive? Well, the one way to do it is to multiply it by a negative. And the reason you're doing it is because that number that you started with is below 0. Okay, so that's really what the absolute value is doing. It's really multiplying negative numbers by a negative and keeping positive numbers exactly as they are. And 0 is also just staying at 0. Okay, so this naturally creates piecewise cases, proof by cases, appearing a lot. And it's very important to learn about this function in this class so you're ready for real analysis. This guy also appears a lot with these symbols, the less than or equal to, greater than or equal to. You'll see why that happens, but it does happen a lot. So it's important to know what these mean and to think about properties that maybe you haven't thought about before. So for example, you would never say that a number is less than itself. But you could say that x is less than or equal to itself just because it's equal to itself. So it still counts as being less than or equal to. And if you have 2 of these guys, x less than y and a less than b, then you're able to add on the same sides and preserve the direction of the arrow, basically. And if you multiply by a negative number, do you remember what happens then? Then it flips the direction. Stuff like that. So I'm probably gonna have more appear out of nowhere once I know which ones I need to use. But these rules, for some reason, show up a lot with absolute value stuff. Okay, so just keep that in mind. Properties of inequalities. Those are called inequalities. I guess I should have said that word. Very fancy word. Okay, inequalities. Okay, so let's start proving some statements about absolute values. Okay, so let A be a positive real number. So just any old number you can possibly think of as long as it's positive. Then for any real number x, two properties I'm going to list at once. The first is that the absolute value of x only equals a if and only if x is a or x is negative a. Not -1, negative a. This or is going to automatically create a proof by cases, as we'll see. It's already going to set it up for us. And then the second property is that the absolute value of a negative x will equal the absolute value of x. So these are properties that I hope you already find believable, but you've maybe never tried to prove them. They're a little bit tricky to prove without cases, so that's why we need cases. So let's think about them for a second before I go through the proof. This is just saying, the first guy is just saying that sort of like the size, you should think about absolute value as a size, like how big the resulting number is going to be the same for a number and its negative. That's the idea. And this is sort of saying the same thing. And you can't, the first one is also sort of saying that you can't have two different numbers with the same size. It's only going to be the same size, same absolute value if it's the positive or negative version of that number. But any other number is going to be a different absolute value. Okay, so let's go ahead and prove. Let's prove the first property. So because it's an if and only if, that means I have to have two directions to my proof. So let's prove the forward direction first, meaning that I'm going to assume that the absolute value of x already equals a. And this is a proof by cases where the conclusion is broken up into cases, which I had not gone over in this section, but we have actually done this kind of thing before, and it's really not as necessary to talk about it specifically because it's in the conclusion. That just means you have to show that one or the other happens, which we've already done. Okay, but I'm still going to call it case 1 and case 2. So case 1, oops, sorry, I misspoke. So where are these cases coming from? That is going to create a proof by cases when you go backwards, but actually this is also going to create proof by cases when I go in this direction, which is right now. So why is that? It's because the absolute value of x is defined in two pieces. So when I want to prove things about it, I want to say two different proofs depending on if I'm in this situation, I'm plugging in a positive number or 0, or I'm plugging in a negative number. So that's where the cases are going to come from. Okay, so the first case will be that and plug in a positive number or 0. Okay, so if I do that, then what can I say? And also, what am I trying to prove? I'm trying to prove that I'll either get a or negative a for x. Okay, and I already know by assumption that the absolute value of x is a. Okay, so if I plug in a positive number or 0, then the absolute value of x is defined to be what? Well, it's in pieces, it's a piecewise function, and when I plug in a positive number, the answer is just that same number. So that's what I can say. So then, it's a very quick proof, absolute value of x equals a, and that's because of this assumption here, and because of this guy, absolute value of x equals x, so x equals a. So in the forward direction, because there's an or in the conclusion, I'm just trying to prove that either one happens, because that makes the conclusion true if either one happens, because it's an or, and I've shown that x equals a, one of the two or statements, in the first case where I start with a positive number or 0. So now I gotta see what happens, because that's not all the real numbers, because x can be any real number. All I've done so far is the positives or 0. So case 2, to cover up all the real numbers, is to check what happens when x is less than 0. Well, then the absolute value of x is defined to be negative x. So now I know that the absolute value of x equals a, just like before. I'm still assuming that up here. And I know that the absolute value of x equals negative x, so putting those two facts together, I get that negative x equals a, which I can multiply by a -1. So I get the conclusion that I want. X equals negative a was the other possibility. And it's true, that's what happened. Okay, so that proves the forward direction. That if I start with a real number and I take its absolute value, and it's equal to a, then that means that the number I started with has to be a or negative a. Okay, so now I gotta go backwards. Which means that I'm assuming that x equals a or x equals negative a. And this naturally establishes a proof by cases. Same thing. What happens when x is a and what happens when x is negative a? Okay, well, if x is a, then what's the absolute value of x? It's the absolute value of a, right? And what's the absolute value of a? Well, what is a? A is already a positive real number. So what happens when I do the absolute value of a positive real number? If it's already positive, it doesn't change. So I'm done, because what was I trying to show in the backwards direction? I was just trying to show that the absolute value of x is a. So I've done that here. I've done what I wanted to show in the backwards direction. That's the conclusion. Okay, but that only covers the first case. What about if x is negative a? That's the other case that I could start with. Well, then the absolute value of x is absolute value of negative a. But what's a is positive. So I guess I should write right here maybe, since a was positive. And here, because a is positive, that means negative a is a negative number for sure. So what happens when you absolute value a negative number? You stick a negative in front of it. So then I get negative times negative is positive a. So I still get the conclusion that I want, which is that absolute value of x equals a. Okay, so this proves 1. I think I'm not going to prove 2 because I want to do more important proofs, but you can try it out if you want. Okay, hope it's believable. I'm going to use it. All right, so instead, we're going to prove more important statements that are a little more interesting. So I hope you can believe that the absolute value of negative x equals absolute value of x. All right, and if not, you can try to prove it yourself for fun. Okay, so here's the next statement. Let a and b be positive, or sorry, no, just a. Let a be, I read the word b as the letter b. Let a be a positive real number. Then, for any pair of real numbers you have, these 3 facts are true. So the absolute value of a real number being less than a is really saying that x is stuck between a and negative a. That's another way to think about absolute values with regards to less than or equal to symbols. So if I change this to a less than or equal to, it would also work. So absolute values, you should think of as like this being less than a number is like trapping it between the positive and the negative version of that number. 2, if you multiply inside of an absolute value, you can just split it up into 2 absolute values. So this is saying, and then this is called something extra fancy. This is called the triangle inequality. If I add 2 numbers together inside of absolute values, that's going to always be less than or equal to adding them up separately. And this is called the triangle inequality. Very important inequality. You'll learn a lot more about it later. One way to think about it is it's really just saying that the shortest distance between 2 points is a straight line. You'll see how that's similar to what this is saying much later. Okay. I keep hinting at things in the future. I guess I should stop doing that. Putting too much pressure on your future professors. Okay, proof of, let's do the first one. So it's an if and only if, so I got to do both directions. And I am going to be using lots of proof by cases again. Okay, so forward direction of 1. What am I assuming? I'm assuming that the absolute value of x is less than a. And of course, I'm still, these assumptions are supposed to the statements. So a is still a positive real number, x and y are just real numbers. Okay, so I want to show that the second part holds. I want to show that x is trapped between a and negative a. So you can think about little mini examples real quick. For example, absolute value of 3 being less than 5 is telling you that 3 is between 5 and negative 5. Okay, but of course examples aren't proofs. Okay, so because there's an absolute value in the hypothesis, that automatically gives us cases to prove. So the first case is that I start with a positive or 0 number. And the second case will be that I start with a negative number. That's the way to break real numbers into 2 halves. Positives and 0, and then negatives. Okay, and then I'm showing it for all the real numbers by doing that. Okay, so if x is positive, what can I say about the absolute value of x? Well, because it's already positive, it's just x. So then I know that this guy is less than, sorry, let me say it like this. So since I already know something else, since this guy is less than A, that's assumed up here, and that thing is just X, that was more of a parenthetical remark, I can just immediately conclude that X is less than A. So that gets me sort of half of what I want to show. So all I'm doing is doing substitution. I'm just replacing X, absolute value of X with X, because they are the same in this situation. What else can I do? So then if I want to show this other part, I need a negative A involved somehow. So let's just think about negative A. So since A is positive, because it's assumed at the very beginning that that's a positive real number, then negative A must be negative. So it's less than 0. But what kind of number is X? It's bigger than or equal to 0. So if it's bigger than or equal to 0, it's got to be bigger than a negative number. So just immediately, negative A is less than or equal to, sorry, it's strictly less than X. So now I've trapped X between negative A and A. So that's the conclusion, and I showed it. So that all happens if X is a positive number to start with, or 0. But what about if X is a negative number? Well, we're just going to do some very similar tricks probably. Let's see, what can I say about the absolute value of X then? Well, now I can say it's negative X, because that's how absolute value works for negative numbers. We just multiplies them by a negative. So then I'm going to do the same thing I did before, which is, because this thing is still being assumed in my hypothesis, what I can say is that the thing replacing it, negative X, is now less than A instead of absolute value of X. I'm just replacing it because they're equal. Okay, so then if I just multiply this guy by a negative, it does that. But it might confuse you because the arrow is facing in a different way now. So if I want to switch the arrow back, I can, but I have to switch the things. It'll be the same. So this is saying that X is bigger than negative A, but I can say that in a different way, which is negative A is less than X. That's the same thing. And that way the arrows stay the same direction. So now I'm halfway done again. I've done this first part on the left there. Okay, so now I probably want to do the same step as before. I probably want to think about, let's see, well, I already thought about negative A, so maybe now I want to think about positive A. Let's see. Oh, I see. Okay, so yeah, this part's easier. So since X is already negative, to start with, that's what we assumed in this case, and A is positive, well, a negative has to be smaller than a positive automatically, so we just immediately get that. So putting these together, we once again get that X is trapped between negative A and A. Okay, so we proved the conclusion holds for positives and 0 and also for negatives. Therefore, we've proven it for all real numbers. So this shows negative A is less than X is less than A for all real numbers X. If the assumption is true, which is this. That's the if part of 1. So now I got to do the reverse. taking slightly longer than I expected. Let's see how long this video is. Okay, so the reverse direction now, I'm going to assume already that that negative a and a trap x, and I'm going to show that the absolute value of x is less than a. That's the reverse direction. And again, I'm just going to do cases. If x starts off as a positive number, then the absolute value of x is equal to x automatically. But guess what? We already assumed x is less than a. So that's why I can just say this immediately. And so I've shown this because I'm just now getting rid of the middle part. I'm just substituting, if you can think about it that way, x with absolute value of x. Case 2 is going to work just as simply. If you start off with a negative number, then when you absolute value it, you get negative x. And we don't immediately get to say less than anything, but we can do this. So since negative a is less than x, that is what is being assumed. I can multiply that guy by a negative number. And then I can replace negative x with absolute value of x. Oops, what the heck? Oh, I didn't change the arrows. Aha, oof, that was close. So right, when I multiply this by a negative, the arrows changed. And then I replaced absolute value of x, sorry, x with absolute value of x. And it is the same as what I want to prove because it's saying that a is bigger than absolute value of x in either case, but I just want to have all the arrows be the same direction, so it looks nicer. And I'll just conclude by saying it that way. Okay. All right, so this proves 1. So the first statement that I said way up here, absolute value of x is less than a number if and only if it's x is trapped between the positive and negative of that number. That's the idea. Proof of 2. Okay, so now we're going to start skipping around a bit because this is going to take much too long. Okay, so 2 is we're trying to show that when I multiply two numbers inside of an absolute value, I can just multiply them separately. And I'm just going to set up the proof. I'm not going to do it. So this can also be done with cases. Except there are 4 cases instead of 2. Why is that? It's because we're dealing with x and y, which can both be any real number. And if I want to think about it in cases, what I can do is say, okay, what happens if both x and y are positives or 0 to start with? Then I just calculate these things. Okay, well then x times y, positive times positive is positive. So that's that. So then when I do absolute value of it, what's the absolute value of a positive number? It just doesn't change. Meanwhile, if I do absolute value of each one separately, because it's already positive, it just stays like that. And same thing with y, it just stays positive. Stays itself because it's already positive. So that means if I do these times each other, it's just x times y. So I'm all done because now I just have this equals this. Right? They're both equal to x times y. So I'm just using xy as a middle thing between the two. Okay, so this is why there's 4 cases. Because what happens if x is positive 0, but then y is negative. So I think I'll just leave the rest for you to try the 4 cases. So then try the rest. I think I'll put this on the lecture problems. So what if x is negative but y is positive? Well, that's actually the same as this case, because they're just changing the roles of which one's positive and which one's negative. Sorry, the equal to should always be with the positive one. There we go. And then case 4, what if they're both negative? Okay. So I want to skip that one because I want to do proof of 3 before I get too tired and crash here. So proof of 3, the triangle inequality. It's much more important. So the first thing that I want to say is just a couple of rules that I'm going to be using. So one thing is that a number is always less than or equal to the absolute value of that number. I hope you can believe me, but you can actually prove it if you want by cases. Basically, if r is already positive, it just equals itself, so it's less than or equal to it. But if r is negative, then it's negative is less than positive always, so it's going to also be less than the absolute value of itself. And that's how you prove by cases. So then, zooming in on this fact and combining it. So this is really just scratch work so far. I really shouldn't have written it in the proof section, but it's okay. So combined with statement 1, which was that when something is less than something else, you can trap it. Sorry, when the absolute value is less than a number, you can trap it between that number and its negative. And then very sneakily, I can just go ahead and make these all less than or equal to's instead. And I could redo the whole proof with this, with the equal to's, and it would all work again. But the idea is, the quick way, is that it really still works because a number is always less than or equal to itself. So if I already proved this, if I was using this in the proof, I could just sneakily say, well, a is less than or equal to a. So then I could just be talking about this the whole time instead, and it'll all work the same. Okay, so I'm just going to combine sort of these two things here to prove the triangle inequality. Okay, so that's not really where the proof begins. So now let's do the proof. That was more of a scratch work. So we want to show, just to remind you of what it was, that if I add two numbers inside of an absolute value, it's always less than or equal to adding them up separately with absolute values. Okay, so how are we going to prove this? So first, use that x plus y is just some number. It's always going to be less than or equal to its own absolute value. That's what we were saying earlier with the letter r. And that means I can trap it between something here. It's going to be very tricky. So this guy is some positive number. So what I'm saying is that x plus y to say this, sorry. Hold on. Oh, I know. Okay, very sneaky trick here. So yeah, that's a positive number. And what I'm going to notice is that the absolute value of x plus y is less than or equal to the absolute value of x plus y. And on the right here, I'm just thinking of that as my some positive number a. And I'm going to be using this property here. Because it's the absolute value of something, it is positive. So remember, a needed to be positive to use this thing. And so what this means is that the guy on the left, without the absolute value anymore, that's what x is here, is now going to be trapped between the positive version of this thing on the right and the negative version of this thing on the right. And then similarly, I'm going to do the same thing for x and y on their own. I'm going to use that same property. So the absolute value of x traps x when I stick a negative in front of it on either side. It's got to be less than or equal to them. Okay, and then I'm going to add these two up. So that was something I did earlier. As one of the properties of inequalities, you can add them all up and preserve the directions. So then factor out a negative here. Now I'm realizing I did some other steps for no reason at all. Whoops. This is actually all you need. Okay, so I'll summarize after. All right, so now what I have is I have a number trapped between a positive and a negative. So this automatically means by the statement of 1, when you trap something between a positive and negative version of a number, this is really just saying like something is between a and negative a, then I can put an absolute value around that middle thing and say that that is less than or equal to a, which is the one on the right. Okay, so actually I did so much extra work for no reason, I just realized. Whoops. We don't need any of this stuff. Let's cross that out. So all we really need is to do this sneaky trick where you realize that a number is less than or equal to itself always. And on the right, you think of it as just a positive number. So then you can use this nice property that if you trap something, if the absolute value is less than a positive number, you can automatically say it's trapped between a and negative a, that positive number. So that's what I'm doing here, except a is exactly the same as absolute value of x, the same as the thing on the left. So it's just a little trick. Okay, this video went on far too long. I'm extremely tired. Okay, so that's going to be it for tonight. See you next time.